So welcome to week 12, where we're basically going to be testing differences between two means and two variances. So these tests are a little bit different than the previous tests, but the foundations are exactly the same. So we're going to be, again, looking at calculating the difference between two means using the Z test, calculating the difference between two means for dependent samples using the T test, calculating the difference between two means for independent samples using, again, the t-test, and calculating the difference between two variances or standard deviations. And this is actually going to be using the F-test. So it's all about the differences in hypothesis testing still. So we're going to be testing the differences between two parameters in this section. So suppose a researcher wanted to study whether there is a difference in the manual dexterity of athletes and band members. In this case, the research question is, does the mean score on a manual dexterity, test given to athletes differ from the mean score on the same test when given to band members. We have students coming in. The researcher is interested in comparing the two means of the groups. So we have group 1 and group 2. And we are not knowing if the mean of all the athletes and band members together differ from a specific value. So thus each group's mean is considered separately. So we have the mean score of the athletes and the mean score of the band members here. And we have the hypothesis. We're testing the null hypothesis that means are the same versus that there are different. So if there is no difference between the means, the mean between them will of course be 0, because you just take mu1 minus mu2, that's equal to 0. If they are not different, subtracting the one from the other will not, of course, yield 0. And then the hypothesis becomes, we have these null and alternative hypothesis. Now there's a few definitions first too that we have to understand. The definition between independent and dependent samples. So two samples are independent when the subjects selected for the first sample in no way influence how the subjects are selected for the second sample. For example, a researcher might select a group of let's say 100 people and randomly assign them to two groups of 50 people each in order to test the effectiveness of a new drug. So one group, of course, is given the new drug. So you have group 1 given the drug, of course. And of course, group 2 is given this placebo. And the people are not connected in any way, right? If you're either in group 1 or group 2, etc. So this is again an independent sample. Now, dependent samples are when the selection of subjects for the first sample in some way does influence the selection of subjects for the second sample. So an example of this, suppose researchers wanted to determine if the average temperature of a person's foot, so you have a person, you have their left foot and their right foot, obviously. So they're testing the temperature here of one foot, and we want to see if it's different, keyword different, from the average temperature of one's other foot, the left foot. So the temperature of the right foot of each person is randomly selected to a group of 25 people, would be measured. Then the temperature of the left foot of each of the same people would also be measured. the sample for the right foot, temperature influences the selection of the subjects included in the second sample. So this is a case of a dependent sample. Obviously, the person is in common in both groups. You have group 1 and group 2. That person is common in both. Testing the difference between two means using the Z test. So previously in the last lecture, we used Z, we used T, and we used chi-squared test to compare a sample mean or variance to a specific, so remember our chi-square was for variance, and our Z and our T were for means. So we use a Z, how do I write this? So we use Z essentially when sigma, the standard deviation, was known. And we use T when sigma was basically unknown. And also for small sample sizes, as n gets larger and larger, approaches Z. So sometimes you could, if sigma is even unknown and n goes very large, then we could also use potentially Z. So we use these tests to compare a sample mean or variance to a specific population mean or variance to decide whether or not to reject the null hypothesis. Now we're just basically going to use the same steps for hypothesis testing to compare this time two sample means or variances. When comparing two means, we may be able to use the Z test, but when the T test is used, we have to decide if the samples are basically independent or dependent. So the assumptions for the Z test to determine the difference between the two means are that both samples are random samples. Samples are independent of each other. So the standard deviations of both samples must be known because we have to know our sigma. If either of the sample sizes is less than 30, the populations must be normal or approximately normally distributed. So the theory behind testing the difference between two means is based on selecting pairs of samples and comparing the means of the pairs. So we look at like these pairs. It is not necessary to know the population mean for either population. For this test, all possible pairs of samples are taken from populations. Of course, it's again, the populations is the key word. The means for each pair of samples are computed, subtracted, and the differences are plotted. If both populations have the same mean, then most of the differences will be zero or close to zero, with occasionally large negative and positive differences due to chance. And then the plotted differences will be shaped like a normal distribution and have this mean of zero. Now, this is a little bit looking messy, and we've done this before, but in a simplified version. So we've done it where essentially the same thing, but now we're taking the variance of the difference. So here x1, so x1, because we have group, let's say group 1 and group 2. And we have our data. X1 bar is just that mean. So that average of group 1. And then of course, X2 bar is the mean of group 2. And this is equal to the sum of the individual variances. So we take the same thing for And then you could honestly understand the difference of the variance is just equal to the sum. So we just add them. Here, this is just the variance divided by N1 of group 1. This is the variance divided by the number and then 2. So when we have this, then we could essentially add them, and then we can take that square root. So this here is our standard error. And it looks like the same thing that we did before if we just remove this part. But we're not going to remove that part. So let's erase it. So it's kind of what we've seen before. And we remember that our test value is equal to our observed value minus our expected value divided by our standard error. Before we had Z was equal to X bar minus our expected value, whatever is in that hypothesis, we can put a not, divided by that standard error. So this is kind of going to be very similar. We're going to have our Z is going to be our difference here, X1 bar minus X2 bar, minus our expected value. But in most cases, this is going to be 0, and I'll explain this, divided by our standard error. Standard error is just going to be this. Okay. So that's what I'm writing here. So there's a formula for the Z test for comparing two means from independent populations. We have that null hypothesis is equal to equal to some difference. So this is just a number. Now, usually we're looking at where mu1 is equal to mu2. So this difference is usually 0. Usually. Versus the alternatives of the hypothesis. Remember that our alternatives can be a two-tailed test where we're checking to see if it's different, greater than, less than, etc. And then we're using this test statistic. So it's just the same thing as last week. This week, it's just about these formulas get a little bit different, and we're in different cases essentially. So now we have this. Instead of our X, we have X1 bar minus X2 bar minus this, and this is usually equal to 0, usually, like I said, divided by that standard error, and that standard error term is this guy. But it's kind of the same as before. So again, remember just like the steps of hypothesis testing. Basically, step 1 is just we state the null and alternative hypothesis and identify the claim. Step 2 is find those critical values. So they're just maybe, it can be a little, depending on our situation, can be a little bit more challenging or not. Compute that test statistic and our p-value. So the test statistic, depending on the case, has a different formula, and make that decision to either reject or to not reject the null hypothesis. So you might want to draw like a little sketch or something to figure this out, and then we summarize the results. Now let's just see some examples. So a study using 2 random samples of 35. So N here, of course, is 35 people. Each found that the average amount of time those in the age group from 26 to 35 years spent each week on leisure activity was 39. So in group 1, they spent on average, let's say 39.6. And then group 2, I'm just taking out information. So, and those in the age group of 46 to 55 years spent 35.4 hours. Assume that the population standard deviation for those in the first and second group were 63. So it says population. So we know that's sigma. So it is 6.3. And the next one is 5.8. Okay, respectively. And at alpha equals to 0.05, can it be concluded that there is a significant difference in the average time? So difference is the key word here. Let's circle it. In the average time each group spends on leisure activities. Okay, so we're going to be checking essentially. So we have group 1 and we have group 2. So this is how they're kind of different here. So we're going to check that they're the same, that mu1 is equal to mu2, or that mu1 minus mu2 is equal to 0. It's the same thing, tomato, tomato, versus the alternative that they're different. So it's like we did before. So we know our alpha is equal to 0.05, and we can find that those critical values, this is a very common critical values, 1.96 and negative 1.96. We know how to find these, I hope. And then you can compute this test statistic. So again, this is the test statistic. So it's x1 bar minus x2 bar. This part here is when they're the same. So it's this value, because we're trying to test the difference. So this part is going to be 0. Then we compute it all. It's just arithmetic, and we get our value, 2.90. Well, 2.90, if we were to draw this, like a little sketch, we don't have to be perfect. We have 1.96 negative here and positive 1.96 here. 2.9 is out here, which falls in this rejection region, because we reject here and we reject here. And we accept here. So null gets rejected out here, the null hypothesis, and it gets accepted in this region. So because it falls in that rejection region, obviously, because it's out here, the null hypothesis is rejected. So this gets rejected in favor that they're different. So we, therefore, going back to the question, then we can write like a conclusion statement. So we conclude that there is a significant difference in the average time each group spends on leisure activities. And you can just see it, like there is a difference in the numbers. So we can support this claim that they're different at the alpha equals to 0.05 significance level. So another example is there a difference in the average daily intakes of dairy products for men versus women? So we have group 1 and we have group 2. We have our sample size of 50, we have our mean, and we have our standard deviation. And suppose this is it doesn't say, but suppose, I'll try to be more clear in the future. Suppose like these are of the population. So we're checking to see if they're the same versus, again, that they're different. So again, we just like compute that test statistic. Again, this is this value here, which is 0. So we can compute all of this. We take the square root and get negative 0.92. So the probability of observing, this is just the P approach versus the test statistic approach. So the probability of observing values of Z that are as far away from Z equals to 0 as we have just by chance if indeed mu1 minus mu2 is equal to 0. This is this P approach. So we can try to find, and we could draw it. Sorry, this is a symmetric curve. I didn't draw it nicely. When this area, when Z is equal to 0.92 and less than. So we could like look these up, look maybe this one up in the table, and we could find this area. And then because there's two areas, 1 and 2, we multiply it by 2 and we get this value. This p-value is obviously greater than 0.05. So this implies not to reject the null hypothesis. And there's not enough evidence to support the claim, because there's p-value is greater than our evidence requires. So here I drew over picture. So again, like this is our Z. Here's our other Z. Just having technical difficulties. 1 second. So then we have like these values. So it's the same picture that I just drew. So there's the formula for the Z confidence interval. So this is the confidence interval between the difference between two means. So it looks a little ugly, but it's kind of what we've seen before. Like, so remember the confidence interval before was basically negative or X bar minus our Z, our alpha divided by 2 times that standard error. So remember the standard error was, let's say, we're using here. So it was sigma divided by square root of n. This is less than our mean, which was less than X bar plus Z alpha divided by 2 times the standard error. Remember, this part was our standard error. So then times sigma divided by square root of n. Again, this part was our standard error. So it's the same, kind of the same thing. This time we're just subtracting x2 bar here. We're subtracting mu2 here, and we're adding this part. So it has kind of like the same sort of pattern. So let's find a 95% confidence interval for the difference between the means of ages of residents and commuting college students. So we have x1 bar, so we're given the averages and the means for the two groups, group 1 and group 2. and the standard deviations respectively, and n is 35 in both cases. So, so suppose we were like checking to see if they were different versus the same. And this could be so we have our alternative hypothesis and our null hypothesis. So we can compute like this messy kind of long confidence interval. And when I say lower bound, I usually refer this as our lower bound. And this part here, this whole thing part here is our lower bound, and this whole thing here is our upper bound. Okay, and then essentially we just plug in the numbers. So we got 22.2 minus 22.3, subtract. This is a 95% confidence interval. So we know how to find this. So we can find our Z here is going to be plus or minus 1.96. It's a pretty famous one. We've done it several times now. So we get this one times the square root of our 3.68 squared, remember to square it, divided by, oh, I think I made a mistake here. This should have been 32, typo, plus 4.7 squared divided by 32. And this value here, mu1 minus mu2, is less than 22.2, subtract 22.3, plus 1.96 times the square root of 3.68 squared divided by 32 plus 4.7 squared divided by 32. Now we compute all this like in our calculator. So it'll take us a few minutes, and we should get this confidence interval. So this refers to a 95% confidence interval. And this again is our lower bound, and this is our upper bound. Now, if we notice, like to understand it a little bit better, this is the difference. So mu1 minus mu2 is equal to 0. So that difference is equal to 0. So we're basically testing to see that are the two groups the same, right? If they are the same, right? If they're different, if the averages are the same, then that difference is going to be 0. So is 0 contained or in this interval from negative 2.2 to 2.2? Is this value equal to 0? Is that question? Well, yes, it does contain the 0 because 0 is between these two, because obviously 0 is less than 2.0 and is less than a negative number. So it contains the 0 is what we're saying here. So the decision is to not reject that null hypothesis. So we don't reject the null hypothesis. Calculating the difference between two samples for dependent samples using the t-test. So this is also could be referred to as the paired samples t-test. So the paired samples t-test is used to compare two means when every participant is in both samples, because the participant, like it's, remember they're dependent. So there's a connection between the two groups. And this is called a dependent samples t-test. So some common situations could potentially be comparing a person's ability to perform a memory task before and after injecting a caffeinated beverage, because that person is in both groups. Comparing a person's weight or BMI before and after engaging in a diet. Comparing a person's mark on a test before and after doing a review exercises. And all like these examples, the person is in both groups before and after. So they're in group 1 and in group 2. So the steps for the paired sample t-test are just almost the same as the steps for the single sample t-test. So it's essentially the same. It's kind of like the Z test. They're basically the same, but the major difference being that we are concerned with a change in the data scores, not the data score itself. So it's not about the individual, it's about this change in the score, this difference. So as a result, we need to find the different score for each participant, and we'll be working with a different type of distribution. So this is the distribution of mean differences. So let's imagine many college students' marks were measured before and after the reading week. And so to determine if they improve. So data will be gathered on a sample of, let's say, 3 people from among this population of many college students. And we notice that each participant contributes data to both samples. So the mark before the break and the mark after the break. So the person is in common with both. So this is why it's a dependent sample. Again, so the distribution would be created as such. So we randomly choose 3 participants from the population, and for each participant, we subtract the first mark from the second mark to calculate this thing called this difference score. Then subtracting in this order is not essential, but will ensure that a positive difference is associated with the mark increase. So we subtract the first mark from the second, and we calculate this difference. I'm just reading it again. Then subtracting in this order is not, of course, essential, but it just ensures that the positive difference is associated with a mark increase, and a negative difference is associated with a mark decrease. So just be careful in setting up which group you subtract from which group. Then we calculate this mean, this difference of the 3 samples, so this D bar. Then we repeat the steps again for each student. So since we're looking at the 3 differences, it's intuitive to note that if there is no difference between the 2 samples, so if sample 1 and sample 2 are the same sample, or therefore the difference would be 0, right? If you take it as if there's no difference, then of course the distribution would center on 0. This situation would coincide with the null hypothesis, and there's no mean difference in the mark. So let's see some examples. So example, like our first part. So let's say we have a behavioral scientist working at Apple who studied, like, let's say 15 volunteers, and they performed on a set of tasks under 2 conditions, while using a 15-inch monitor and while using a 42-inch monitor. The latter of which allows multiple programs windows to be visible at one time. So it's sort of like when, and have like a very large monitor, and you can open a whole bunch of windows and you can watch maybe a movie in a corner and then do something else on this side and you're multitasking, versus someone with a 15-inch monitor who might not be able to open all those windows up at one time. So does the larger screen help people essentially increase their time performing tasks? So using the data, we're going to perform this paired sample t-test with a 0.05 p level or alpha level. It's kind of like the same thing, to determine if people who use the larger monitor perform differently than those who use the smaller one. So we have, like, let's say 5 people, and we have the time to complete the tasks on the 14-inch monitor in seconds, and the time to complete the tasks on the 40-inch monitor in seconds. So does having like a larger monitor help? So we're kind of like reduce the time. And we can kind of see by the data that the time has been reduced for the second group. It is less than the time in the first group. We can kind of see this by analyzing, just quickly glancing at the numbers. But let's like analyze it a little bit further than that. So we have our two groups or two populations. I should probably say group 1 and group 2. So in group 1, the participant times using are the 14-inch monitor. And in population 2, the participant times are using the 42-inch monitor. So the comparison distribution is this distribution of mean differences scores based on the null hypothesis. The hypothesis test is a paired sample t-test because we have the two samples of scores where participants are not of both samples. So step 2 is, well, it could have been actually step 1, that this null hypothesis. So the mean time for population 1 and the mean time for population 2, and we're checking to see if they're different. So that's the alternative versus the null hypothesis that they're the same. So this is where it gets a little bit more confusing with the dependent sample. So we fill in this table to help determine the mean difference, D bar, and the standard deviation. So we have our data. This is just our X and our Y data copied down in the first two columns. And then we calculate that difference. So our difference, in this case, we could go Y minus X, let's say. We could probably do it the other way. So we take our Y, so 111 minus 122. So this is negative 11. 116 minus 131, negative 15, and so on. So that's our D. Then we calculate D bar. There's a bar over here, over these Ds. Not sure why it didn't show up nicely. So D bar is equal to the sum. So we add all these up and divide by 5. I put dot, 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 but it's negative 11, subtract 15, subtract 14, subtract 4, subtract 11. And then we divide by 5. And our average for this difference is negative 11. Then we take D, which is negative 11, subtract negative 11. So this would be, let me write it here. So it'd be negative 11, subtract negative 11. So this would be 0. The next one is negative 15. If you punch it in your calculator, negative 15, subtract negative 11 would be negative 4, and so on. Negative 11, subtract negative 11 again with 0. So we get these values and we square it. 0 squared is 0. Negative 4 squared is 16. Negative 3 squared is 9. And 7 squared, of course, is 49. Now we find like this S, the standard deviation. So we did all this work. So we sum all this up. So we sum it up of basically 16 plus 9 plus 49. Calculate this. So 49 plus 9 plus 16, 74. So we have this part here is 74, our numerator, divided by, well, we have 1, 2, 3, 4, 5, 5 minus 1. And then we take that square root and get 4.30. With this value, then we get the standard error. I should maybe write standard error of that difference. I don't want to confuse you maybe with too much notation. SD is like standard error of the difference, which is just S 4.301, standard deviation, divided by the square root of n, and we get 1.924. Now, this difference is the mean of the difference is going to be zero, almost zero for every pair t-test, usually zero. Because what I mean by this is, suppose the samples were exactly the same, because this is what we're going to be testing. If they were the same, if this was 120, 131, etc., then the difference, of course, is going to be zero. And this is what we're testing. What happens when they're the same versus when they're different. Now we can like look this up in our table to get the critical values. Okay, so we have our alpha of 0.05. So we take our calculator, 0.05 divided by 2 is 0.025, and our degrees of freedom is 5 minus 1, 4. So we go here and we see it's 2.776. So this is how we get that critical value again for that t-test. So it's going to be plus or minus 2.776 and 2.776 on this side. Now we calculate this t-test. So the t for this one is going to be a little bit different, but kind of the same. So our t-test is going to be d bar, so that average that we computed, minus our u, our mu d, but that's zero. That is that. So this value is that difference of the means that we want to calculate. I'll write it up here. So this is mu1 minus mu2, which is 0, because we want to test this, this difference. So it's basically for the hypothesis testing, so for the null hypothesis, divided by that standard error. So this is maybe SD. You could use the notation SD, or you could use a standard error of D. That might make more sense to you. And we calculated this in the previous slide. So then we calculate it and get negative 5.72, which is out here. So this is obviously in that rejection region, right? So we therefore reject the null hypothesis. And it appears there is a difference in the mean time it takes to perform a task on 15 or whatever it was, I think 14 and 42-inch monitors. Now let's construct a 95% confidence interval for the population mean difference and the completed time. So we know we have our critical value of 2.776. We have our S, and we have our square root of n that we calculated previously over here. So we have this, we can just then take that number from what we did and we calculated 5.341. So then D bar subtract E is less than this, which is equal to 0, or mu1 minus mu2. And we calculate this, D bar plus, etc. And you see, if we do this, 0 does not fall in this 95% confidence interval. So when they are the same, so the 0 isn't in the confidence interval. So this doesn't contradict. So this is the same as so rejecting that null hypothesis. So we calculated this confidence interval, and when the means are the same, that's not in the confidence interval. So then we can therefore reject, go back, we can reject that they are the same, and we can conclude that there is this difference. So this is another way of doing it. Another example, suppose a salary wizard is an online tool that allows you to look up incomes for specific jobs for cities in Canada. And it doesn't really matter, but like, let's say this is made up data of like Oshawa and Whitby, and we have like different careers. Like these careers don't really matter, but let's perform a test on it. So we're going to conduct this paired sample t-test to determine whether income in one of these cities differs on average from income in the other, and use a two-tailed test in a p-level, p meaning alpha of 0.05. Sometimes they say p-level, sometimes they say alpha. I'm just going to be flipping back and forth. So we have our two groups, group 1 and group 2. Group 1 is obviously salaries from Oshawa, and group 2 is salaries from Whitby. And we have our mean of populations 1 and 2. And then we are comparing, of course, to see if the salaries, to see if it's the same or if it's different. So we could, this is the part where I would start to say, use Excel here. So during the break, I simply just copied that data into Excel. So in Oshawa, so I put all the data here, X and Y, and then I just took the difference. So in order to put calculate the difference, you just create a formula. So you write equals B4 minus A4, and then you do auto scroll. So in this lower right corner, you put your cursor and you just copy it all down, and it auto fills, and you drag it down. Like suppose I deleted this. Sorry. Delete, delete, delete. So what you do is you write the formula, and then you copy it all down, and then you press enter, and it just copies it down. The average is simply, there's a function equals average. So let me do it. So you write average equals, and then you go to your cell, and then you scroll down, press enter. Here for the standard deviation, again, there's two of them, standard deviation. So it's STD EV, and there's the population and the sample. This is the sample. So you do .s, go to your cell, and then you scroll down. Oops, I made a mistake. Or you could just type it in. Press enter. And then you have your average and standard deviation instead of writing it out. So this is how we get the average of the difference and the standard deviation of this difference. This is the difference. If we don't want to compute it, just use Excel. Then once we calculate our S, we can divide by our square root of n. Here n was 1, 2, 3, 4, 5, 6. And we calculate 438.83. Again, this difference, remember this part is just from here. So this is when mu1 minus mu2 is equal to some d, and d is usually equal to 0. So that is the mean of that difference, is usually equal to 0. And that's what we're, the expected value, and that's what we're trying to test. So once again, we find that p level, for 0.05. We can look this up in the table. So our alpha level was 0.05. It's a two-tailed test because we're looking at for the difference. So we divide by 2, so it's going to be 0.025. And our degrees of freedom, because n was 6, so n minus 1 is 5. So it's going to be 2.571 right there. So we have our t, we calculate our t, of course, is our d bar minus 0 divided by that standard error of that difference, which we calculated previously on the other page, is 18.04, so very, very far away. So, you know, if we so 18.04 is all the way over here. So 18.04, far away. Obviously, it's not in the, it's obviously in the rejection region, right? Because it's so far away from where we would accept the null hypothesis. So we're going to reject that null hypothesis clearly. So it appears there is a difference between the mean salaries in both Oshawa and Whitby. Here's another quick example. It's kind of long to read everything, but suppose there's a new counseling program at a hospital to reduce anxiety of patients, so before heart surgery. And so this test of anxiety is given to the patients, and each patient participates in a series of counseling sessions with a staff psychiatrist. At the end of the counseling sessions, each patient is retested to determine anxiety level. The following table indicates the results for a random sample of 9 patients. So we have 9 patients. So higher scores mean higher levels of anxiety. Assume the distribution of differences is mound shape and symmetric. Can we conclude that there is the counseling sessions reduce anxiety, and use this p level of or alpha level of 0.01. So we have the population 1 and 2, and we could say population 1, we call it A. So because let's say this is A, so the scores after counseling sessions, and the scores, and B, let's say, is the scores before counseling sessions. So we just wrote it this way, so we could take that difference, A minus B, because we want to see if like there's a positive relationship, like does the anxiety go down? So we have the mean of population A and the mean of population B. And then we take that difference. So we subtract 76, subtract 122, et cetera. And you can fill out the difference, obviously. Now, we could, of course, just plot that, put that data into Excel. And so again, just use Excel, like I showed you in the previous question. And we can then get the average, which is negative 33.33, and the standard deviation of 22.92. We get like these numbers, 22.92 divided by square root of 9, and we get 7.64. And we're testing to see if the null hypothesis is, the difference is equal to 0. So if the means are the same. So here, we're constructing a 99% confidence interval. So a 99% level. So our P level is 0.01. So this corresponds to 99% of the data underneath the curve. Now our degrees of freedom are 8. So we look this up in the table. So for our alpha or P, I use it interchangeably. We're looking at 0.01. Our degrees of freedom, I believe what was it? 8. So it would be right here at 2.896. But remember, this question, we're looking at, it's a left-tailed test. So it's going to be negative 2.896. Because it's going to be on this side. The table only gives us positive values, as you notice. The t-table gives us only positive values, but we want the negative value over here, and due to symmetry, we know that this is going to be negative 2.896 on this side. So we find that critical value. Then we can simply compute this difference to see if it has changed. So we calculated this before in the previous slide. We get negative 4.36. So that's on this side. So that is our t-statistic if we've set this all up correctly. So therefore, we can reject this null hypothesis. It's not in the rejection region. So it appears that the sessions did reduce the mean anxiety level of patients. Now, we can set this up this way, like A minus B, and just so it's properly set it up on the axis. So we don't get confused to see if like it would correlate, how do I say it? Like if it, like you see it would go down after counseling sessions. So this would indicate that the difference would be negative. So this will correlate when plotting this properly. Testing the difference between two means of independent samples using the t-test. So before they were dependent, now they're independent. So test the difference between the two means for independent samples using this test. So the t-test used to test the difference between the means when the two samples are independent and when the samples are taken from two normally or approximately normal distributed populations. So the samples are independent samples when they are not related, of course, that's the key word. And we will assume the variances and therefore the standard deviations are not equal. The formula for the t-test uses the standard deviations of the samples to find the standard error of the difference between the two means, since the population standard deviations are not known. Of course, like these are not known because we're using a t-test. So we assume, again, like there's assumptions that the samples are random samples, the samples are independent from one another, and the sample sizes are less than 30. The populations must be normally or approximately normally distributed. So again, it's like what we just did before, kind of. However, there's a little bit of a difference. So we have so we have our t-test, we have like the difference of our sample means minus what we're testing divided by our standard error term. And here, instead of like what we did with our Z, we had our sigma, we have S. Now the variances are assumed to be unequal. And we have the degrees of freedom are equal to the smaller of n1 minus 1 or n2 minus 2. And we assume that the assumptions are met. Now, in different textbooks, they use a different formula. I just want you to be aware of it. So if you see something like our textbook uses this formula. So I'm going with what our textbook does. I have seen it where it's like a weighted average, and it is a bit more a complex calculation than what we're going to be doing. So just to be aware that there is another formula for independent samples for the t-test. this is I think this is a simplified version. It's sort of, it's like the cosine law. Well, the cosine law, if you remember it from high school, that's like a little bit complex. The special case of the cosine law is Pythagorean theorem, which is this c squared equals a squared plus b squared. That's a special case of the cosine law. This is just like a special case of something a bit more complex than what our textbook covers. So you're aware, right? Like I'm just letting you know. Okay, so upright vacuum cleaners have either a hard body type or soft body type. Shown are the weights in pounds of a random sample of each type, and alpha is equal to 0.05. Can be concluded that the means of the weights are different. So we have the hard body types, the soft body types, and we have our data respectively. And we can count. So 1, 2, 3, 4, 5, 6. And remember, so we take the smaller of them. So n here is 6. Here, 1, 2, 3, 4. So 4 times 4 plus 1, 17. So here is 17. So again, it's the same thing as we've previously done before. So we're going to see if there's the keyword here. Can we conclude that the weights are different? So when we immediately see that we're different, we know that we're going to be doing a two-tailed test. So we can construct, so the alternative is to see if they're different versus the means are the same. The degrees of freedom for the smaller one is just 6 minus 1, which is 5. And we're conducting this test at alpha equals to 0.05, and we can find this critical value looking it up in the table. So the degrees of freedom, 2.571. So we could type this in, and we can, like, again, I would get these numbers from Excel. I showed you previously, you type them in. So you get, this is from the first group, and this is the standard error. And you can do this to yourself, and this is the second group and the standard error for that. And we just compute that t, so which is 1.495, plugging in all the numbers. So this value, of course, if we had to draw it, so this is like our 2.571, and then there, because it's two-tailed test, 2.571. We have like this area in here. So 1.495 will be here. So we do not, of course, reject that null hypothesis because it's in the exception, except the null hypothesis region. We accept all in here, and we reject outside. So there's not enough evidence to support the claim. Now we can create confidence intervals for the difference of these two means. Remember, our sigmas are here for their t-tests. Again, t-tests, our sigmas are unknown. So our independent samples can be calculated in this way. It's the same idea over and over again. X1 bar minus X2 bar minus T alpha divided by 2 divided times the square, the standard error term essentially. So this again is our standard error term. Less than mu1 minus mu2 less than X1 bar minus X2 bar plus T alpha divided by 2 times this standard error. And again, the variances are assumed to be unequal, and we take the degrees of freedom to be, again, the smaller value of n1 minus 1 or n2 minus 1. Now, this is where it does change, where this is the part where it is a simplified part, because it's actually like a weighted average, so you actually compute both of them. It's a bit, I guess, too much. Anyways, suppose there's top 100 cities with the oldest houses. I really like old houses personally. And so there's Indiana, Whiting, Indiana. They lead essentially with the number of houses being 600 or 66.4 years. Further down the list is Franklin, Pennsylvania, with an average house of 59.4 years. Researchers selected at random 20 houses in each city. So, and here is, and here is 20 houses in each city, and obtain the following sample data. So the sample mean age and the sample standard deviation of both, and selecting 20 houses at random. At alpha equals to 0.05, can it be concluded that the houses in Whiting are older? Well, and construct a 95% confidence interval for the difference between the two mean samples given this data. So we have all this data. So we have our S's, we have our sample mean ages, etc. So we're asking ourselves, are they the same versus are they, is one older? Is this one, so this is like, let's say group 1 versus group 2, is this older than this? Okay. So we can test that they're the same versus that they're older. So we can calculate like this confidence interval, right? And remember this part again, I keep repeating it, but is where it's equal to 0. So essentially we put in our data. Here are our X. This is our X1 bar. This is our X2 bar. And then these, just double checking, our S's, our sample standard deviation, our S1 and our S2. And then we essentially compute it. Hold on. And we find this number, alpha equals 0.05 in our table. So let's do that. So again, it's a two-tailed test. It's 0.025. We look in their table. So our degrees of freedom is 19. So 2.093 is right here. So here we're going to be testing the difference between two variants in this section 12.4. So sometimes we're interested in comparing two variances or standard deviations. So for this, we use an F-test. The F-test is not the chi-square test, although there's lots of similarities. So they're look very similar, but they are a little bit different. So this is where we use a comparison. So there's just, again, characteristics of the F distribution. So the same as the chi-square distribution, the F cannot be negative because variances are always positive or 0. So again, we see our values are positive. The distribution is positively skewed. The mean value of F is approximately equal to 1. So that's a little, so make note of that one. The F distribution is a family of curves based on the degrees of freedom of the variance of the numerator and the degrees of freedom of the variance of the denominator. So we have 2 degrees of freedom. So it's a little bit different, and we'll see this. So comparing 2 populations is where we use the F test. So we make inferences about this ratio of the population variances. Again, this is a ratio of one variance over the other variance. We choose 2 independent random samples of size n1 and n2 from the normal distributions. And if the 2 population variances are, so for them, we use this F statistic here. So F is equal to the variance of 1 divided by the other variance. This has this F distribution of degrees of freedom of n1 minus 1 and degrees of freedom n2 minus 1. And so n1 is the sample size from which the larger variance was obtained. So the larger of the 2 variances, so this is a key part here. So where the larger of the 2 variances is placed in the numerator, regardless of the subscript. So you find out whatever the variances are, and put the larger one here versus whatever the smaller one here. So the larger variance, again, I'll repeat it, goes in the numerator, and the smaller one goes in the denominator. And we have, again, of course, our degrees of freedom. So we use this thing called this F table. So we have the degrees of freedom of the numerator is basically the first row or along this side. And the degrees of freedom of the denominator is this first column. So these rows down here versus these columns, however you want to think of it. I hope that makes sense to you. And then we have different alphas. So for alpha like 0.05, let's say, degrees of freedom of, let's say, 21 for the denominator, you would look down here, you see, okay, 21. And then the degrees of freedom of, let's say, the numerator is 15, and we get that value here. So when the degrees of freedom of the values cannot be found, a little side note, cannot be found in the table, the closest value on the smaller side should be used. For example, 14 degrees of freedom of the numerator falls between the values of 12 and 15 on the table, thus 12 should be used. So if we want 14, you don't go up to 15, you go to the smaller one, which would be 12. Let's see this in the table. So the F tables have the numerator, the degrees of freedom for the numerator are in this first row, or the columns essentially, and the degrees of freedom for the denominator is in this first column, or the rows respectively. And there's different tables for each alpha, and you can see the picture. So the F distribution has the degrees of freedom for the numerator and the degrees of freedom for the denominator in brackets here. And you can see the pictures, of course, to analyze this. And alpha is that area underneath the curve. So there's different tables essentially for different alphas. So this is alpha at 0.10. This is alpha at 0.05. This is alpha at 0.025. As 0.01, etc. So like first you have to find your alpha. So the questions has alpha at 0.05, and we have the degrees of freedom of the numerator is 15. So we have our 15, go down, And our degrees of freedom of our denominator is 21. So we find our value right there. It's 2.1757. So we found it. Oops. Okay, so for this example, the F table gives only the upper critical values of the tests of the F statistic for the given pair of like these degrees of freedom. So we're going to look this up for the degrees of freedom of 10 and 10. So you find your alpha. So alpha is 0.025 and it's 10 and 10. So the value here is 3.7168. So assumptions for testing the difference between two variances. So the samples must be random, of course. The populations from which the samples were obtained must be normally distributed. The test should not be used when the distributions depart from normality. Minor departures from normality will affect the results of the test because the standard deviation is not resistant to outliers or extreme values. And the samples, of course, have to be independent of one another. So here is another example. So a medical researcher wishes to see whether the variance of heart rates in beats per minute of smokers is different from the variance of heart rates of people who do not smoke. So we have two samples collected. They're independent because someone's either in this group or that group. They're not possibly in both groups and they're not dependent on each other in any way. So we know it's independent from kind of like the question. Use the alpha of 0.05 to check to see if there's enough evidence to support the claim. And assume that the variable is normally distributed. And sometimes we want to check, sometimes we're doing we want to check the averages of something. Before we do that, we want to use the F statistic to check on the variances. So this time with the null hypothesis, we're going to see, are they the same versus are they different, the claim. So we can find this critical value. Remember our alpha here is 0.05. And we see because of this part, or remember it's a two-tailed test, just to remember. So there's an area of alpha divided by 2 on one side because of the two-tailed test. So that's 0.025 on the left and the right. So we look this up in the table. And so back to the question, we see that the smokers, N here is 26 and 2 is 18. So the degrees of freedom here is N minus 1. So it's just 26 minus 1, which is 25. And this is for this one. And the degrees of freedom for the second one is N minus 1, which is just 18 minus 1, which is just 17. Okay, just remembering that. And we go back to the definition back here. So remember, the larger of the two variances is placed in the numerator. So the larger one, so of the two variances, so this is the larger one. So this is placed in the numerator. Okay, so the degrees of freedom of the numerator, because this is the largest one, is 25. And the denominator is 17. That's a smaller one. So we look this up in the table. You look up alpha equals 0.025 in the table. Remember our alpha is the shaded area. Our numerator is the largest one with the larger variance. So that was 25, but 25 isn't in the table. So you go with the smaller one, which is 24 right there. Sorry. And then we scroll down for the denominator, that's 17, and we just read it across. So we get 2.559 So we get our critical value of 2.5598 something. So this is rounded. So, and this is using this degrees of freedom of 24 instead of the 25. Now we can compute the F. It's the easiest one to compute actually, because it's just going to be 36 divided by 10, 3.6. So of course we could like kind of draw like a sketch. It's kind of harder at this point to draw like these sketches, like how do I draw it? Whatever, that's not a great drawing. Okay. So our critical value, let's say, is 2.56. And we have our F statistic of 3.6 here. So we reject the null hypothesis, since this is the accepted area and this is in that rejection area. So reject the null hypothesis since this is larger. So there is sufficient evidence, therefore, to support the claim that the variances of the heart rate of smokers and non-smokers is different. And I think this is our last example. Yeah. So a researcher wants to compare the variances of the height in inches of four-year college basketball players with those of players in junior college. Okay, so we have a sample of 30 players from each type of school is selected, and the standard deviations of the heights of the players are, so we have the heights respectively. Okay, and we have it's 30. Okay, each. Okay. So this is the larger one, so we know it's going to go on top, and this is the smaller one. At the alpha equals 0.02 level, is there significant difference between the variances of the heights in the two types of schools? So we check that the null hypothesis is that the variances are the same versus the alternative, or one here, I should put an A, that there are the same or different. Because again, keyword difference. So of course, again, this is a two-tailed test. So we find our alpha is equal to 0.01. So we divide it by 2, and we're looking up in the table of 0.01, one part of that area on the left and the right. So we look up in the table these values. So be careful in the tables, because here I have it's alpha equal to 0.1, but if you keep scrolling, here's the alpha that we want of 0.01. And now we look them up in the table. What is the value? So here we have 29 as the degrees of freedom, but we go to the smaller one, which is 24. And then we go all the way down. On the denominator, they actually give us all the values. So we go to 29 and we can read it across, which is 2.495. So we get 2.49 here, let's say. And we used the degrees of freedom of the numerator was 24 was used because we couldn't find the other one. And we couldn't find 29, but the denominator we could find, which was 29. So we calculate like this F statistic. Again, it's the easiest one. Again, this is the larger value. This is the smaller one. We got 1.68. So 1.68 does fall in the null hypothesis region. So we do not reject that null hypothesis. It does not fall in the rejection region, obviously. So there is not sufficient evidence to support the claim that the variances of the heights of the basketball players at four-year colleges and junior colleges are different.